What happens when generation is treated as optimal transport? Raw EEG is synthesized as a flowing signal, and memorization is studied with exact statistical theory. In this episode, we dive into three striking papers that push generative AI in very different directions. One reframes sampling as value-driven transport, another teaches transformers to generate clinical EEG with remarkable realism, and a third reveals when models memorize, converge, and truly learn latent structure. Together, they paint a vivid picture of where generative modeling is headed next. Let's explore the first paper, Generative Modeling by Value-Driven Transport. Generative modeling by value-driven transport reframes sample generation as a discrete-time stochastic control problem for Wasserstein. Optimal transport then solves the resulting constrained linear program with a primal dual algorithm that learns a scalar value function rather than a transport policy directly. The key novelty is the value-driven transport, VDT policy. Pi hx equals x, h plus 1, negative 1, v hx, which is derived from the LP dual, and provably recovers the optimal straight-line interpolation paths of dynamic OT. The final time dual variable also acts as a discriminator, enforcing the target distribution. Training is simulation-free. Each mini-batch is initialized with an approximate coupling. Particle clouds are refined by Wasserstein gradient descent, and a single neural network parameterizes the value function using no-learn trajectory simulator. On 2D benchmarks including 2 moons, S-curve, 8 Gaussians, and moons, 2, 8 Gaussians. OT initialized VDT matched or approached state-of-the-art flow and Schrödinger bridge baselines with 1-0 step generation, essentially matching 1-0-0 step generation. For example, on moons 2, 8 Gaussians, it reduced Wasserstein to error from 1.365 to 0.626 when moving from 1 to 10 steps while preserving path energy near the oracle. On MNIST, the same framework handled paired deblurring, unpaired MNIST to MNIST translation, reverse generation, and classifier-free guidance, showing that OT-style straight path geometry can support conditional and bidirectional generation within one unified control-based model. Let's explore the second paper, Let EEG Models Learn EEG. Let EEG Models Learn EEG introduces Just EEG Transformer, or JET, a conditional flow matching model that generates raw multi-channel EEG as a continuous trajectory rather than through discrete denoising. Built on a transformer backbone with patch-based tokenization, adaptive layer normalization, and class-balanced sampling, JET learns a vector field that transports Gaussian noise to the EEG distribution while preserving channel identity and long-range temporal dependencies. Its core novelty is a set of structure-preserving constraints, an L1 reconstruction loss motivated by a Laplacian prior, a statistical consistency term matching per-channel mean and standard deviation, and spatial-temporal regularizers using temporal total variation and Pearson correlation. On 3 TU-H EEG corpus benchmarks, TUAB, TUEV, and TUSZ, totaling more than 10,000 clinical sessions. JET reduces TS-FID by 42% versus EEG GAN on TUAB, 324.18 to 188.27, 47% on TUEV, 448.65 to 235.86, and 45% on TUSZ, 274.37 to 151.27, while reaching silhouette scores of 0.995, 0.983, and 0.987, and downstream accuracy gains of plus 2.9%, plus 3.2%, and plus 1.7% when augmenting the CBRA-MOD classifier. The paper's analyses show that JET preserves 1. F-spectral scaling, alpha band peaks, non-stationary amplitude envelopes, and heavy-tailed amplitude distributions, and its ablations reveal that Gaussian noise initialization is essential. Zero-noise training catastrophically degrades TS-FID to over 1,500, confirming that a non-degenerate base distribution is necessary for valid flow-based EEG synthesis. Let's explore the third paper, Memorization, Convergence, and Generalization in Generative Models. Maillard and Gold give an asymptotically exact theory of memorization, convergence, and latent recovery in linear generative models using a spiked Wishart Gaussian data model with covariance sine equals I plus beta 1 and a regularized covariance estimator sampled through sines equals sine 1/2 Z They show that memorization, quantified by the maximum training sample overlap M, is a small load phenomenon. For large N, it decays as M is approximately equal to sqrt2 log n, n1 plus sigma squared, n, so the model stops reproducing individual training points on the scale n equals theta 1. By contrast, the convergence overlap Q between two independently trained models with the same latent Z turns on only when NYD and is governed entirely by the Marchenko-Pastor bulk spectrum, with Q1 as gamma equals n divided by d infinity. The main novelty is that Q does not detect whether the principal latent direction U has been recovered. That requires a separate overlap Q between top eigenvectors, which obeys a BBP transition at gamma beta equals beta 2 and is 0 below threshold. They then connect Q to the Kullback-Leibler divergence and Q to the maximum slice distance, showing that output agreement and latent factor recovery are mathematically distinct objectives. Extending the analysis to power law spectra, they explain why real images from Celeb A and ImageNet make the naive Q misleading and define a rotated overlap Q wine in Fourier space that recovers a sharp transition near gamma is approximately equal to 1. In diffusion experiments with a UNet on Celeb A, Q and QZ reproduce the memorization to generalization transition and latent recovery behavior observed by Kodkodaye et al., ICLR 2024. That's a wrap on today's AI paper highlights. Thanks for watching.